These are the titration notes. It will be helpful to have a calculator handy throughout these notes. So, what is titration? Titration is a lab technique that adds a solution that has a known concentration to a solution that has an unknown concentration until an equivalence point has been reached. So, our goal with titration, and this is a lab process that we use specifically with acids and bases, is to determine an unknown concentration uh, through a neutralization reaction. And so, what does a titration setup look like? So, we're going to see some new lab glassware that we haven't worked with before. Specifically, we see a burette. You could see it spelled either of these ways. And burettes are usually filled with a basic solution, like potassium hydroxide, calcium hydroxide, and we generally know the concentration. So we choose a solution we know the concentration of that is a base. We put it in this burette. Then the burette has a little stopper here where we can twist this and we can let some of that base solution go into an Erlenmeyer flask easily. And we can put in a drop at a time, we can put in milliliters at a time. But that burette allows us to measure exactly how much we put in because we don't know how much of that base we're going to use. In the Erlenmeyer flask, we use an Erlenmeyer flask here instead of a beaker because that way when we are swirling to mix the base that is here and the acid that we put in that flask, it just reduces the amount of spillage. But you could just as easily use a beaker there as well. Usually in the Erlenmeyer flask is an acidic solution. So we usually put an acid in our Erlenmeyer flask and a base in our burette, but you could always switch it and have an acid you know the concentration of and a base you don't know the concentration of in the flask. But usually base goes in the burette and then an acid in the Erlenmeyer flask, and we don't know the concentration of that. So our goal is to find what is the concentration of our acid based on making a neutralization reaction occur. And in order to do that, we see this pink here, we are going to use an indicator, and there are a lot of different indicators. We often use phenolphthalein, and that indicator is one color when the solution is acid, one color when the solution is base. And so because of the properties of that indicator chemical, it allows us to see when we get what we want. So how do we read a burette? Because it's not like a normal graduated cylinder. Graduated cylinders have 0 milliliters at the bottom, and then we fill them up and we measure how much of that liquid that we have. With the burette, we actually have the opposite. So a burette has an initial reading at the top. So we start at the top with that, and any burette has a reading of 0 at the top, and then the measurements increase as we go down. And then those increase so we can easily measure how much solution has been let out of the burette while performing that titration technique. And so we have 0 at the top, which means that as we're measuring, we need to pay attention to, okay, if this is 0 to 1, when I'm looking at this initial reading, well, I've got my 0, here's 1, here, 0.1, here's 0.2. And so this reading, again, reading from the meniscus, the bottom of that curve, we need to estimate that this is between 0.2 and 0.3, which is opposite. Whereas if we were reading on a normal graduated cylinder, we would have 0.1 here and 0.2 here. And so if this something sorry, it just changes how we are measuring with that. And so this one, we would have an initial reading of 0.27. Through the process of titration, you let out some of this solution. And so then we're going to have solution in our Erlenmeyer flask. Then we compare our final volume here, and we subtract it from that initial volume or that initial reading in order to find how much of the solution was dispensed with that. And so as we're kind of looking at it, that additional solution that ends up there is that solution that originally was here. Or I guess it was originally at the bottom, but now all of it's shifted down. So let's practice reading a burette. So we've got 2 readings here. And usually, depending on how many titrations you have, your initial reading might be close to 0 if your burette is full, but it might not be. Once we can read our initial and final volumes, we can subtract to find out how much is used. And so my volume initial, I'm going to go over here and remember that we measure from the bottom of the meniscus. So that meniscus is that little curve. And so kind of lining it up with the bottom of this curve that's caused by that surface tension. Here's my 0.0. This here is my 1.0. So that means this is 0.5. And so as I'm looking at this, and it's kind of hard to see that there's a line here, we've got 0.1, this is 0.2. And so we're kind of between 0.1 and 0.2. So I'm going to estimate that this is at 0.05 milliliters because it's between 0.15 milliliters because it is between that 0.1 reading, which is right here, and that 0.2 reading, which is right here. So estimating that 1 digit past the markings we have. So 0.15 milliliters, and burettes measure in milliliters. We'll see kind of with our calculations what ends up happening, but we don't use super large amounts, and so milliliters is usually plenty, or is usually the unit we use. And then let's do what is the final reading of our burette. And so some of the solution has been let into that Erlenmeyer flask until we get the desired result. And now as I look here again, we're looking at the meniscus. So looking at the bottom of that curve, as I'm looking at my reading here, this is my 22 milliliters. So that's 22.0. Here's 23.0. Here's 22.5. And so as I'm looking here, this looks like 0.1, 0.2, 0.3, 0.4. So we are between 22.1 and 22.2. And to me, it kind of looks about halfway. So I'm going to just say 22.15 for my final reading. And then how do I figure out how much was actually used? I go final volume, 22.15 milliliters, minus that initial volume, 0.15 milliliters. And so it looks like we used exactly 22 milliliters is the volume of whatever is in our burette used. And most often that's a basic solution in our burette, but it could also be an acid. All right, so what are our steps? How do we perform this titration process or titration lab? First, that burette gets filled with a known concentration solution. Usually it is a base solution, but we always know what the concentration is. You're going to record the initial measurement of the filled burette. Then you're going to measure out the necessary amount of the acid. And so we're going to measure out how much acid we have using in kind of the milliliters. And so you're going to measure the volume of the acid in milliliters, and you're going to want to record that. Then that goes into your Erlenmeyer flask. We add 2 drops of indicator to our Erlenmeyer flask. That's often phenolphthalein. There are other indicators, but we use phenolphthalein most often, and so that is going to have that pink color. And then with that Erlenmeyer flask under our burette, we add the burette solution, which is a base solution. into our Erlenmeyer flask by turning that stopper. Once pink starts to show, we're going to slow down how much solution we're adding, kind of going 2 to 3 drops at a time and swirling that Erlenmeyer flask to mix the solution. And so while this is happening, our indicator put into our acid is still going to be clear. But then when we start to see that pink, that's an indicator that we're getting close to that titration point. The titration is complete when our solution in the flask stays a very light pink color. So we want that pink to just barely hold on. Once we've reached and we've determined we have a light pink color, this picture is actually too dark. We'll look at the pink colors on the next slide. Once we are done, then we get our final reading from our burette, and we want to write that down as well. And then we can calculate the amount of solution that was added from the burette, which is what we did up here. And then from there, we will have the known concentration of our base. We know how much acid we started with. We have found the amount of base that was used through that calculation. And then we'll be able to actually figure out what concentration the acid is that was in our Erlenmeyer flask. So what does it mean if we see a dark pink? What does it mean if we don't see pink at all? So good pink versus bad pink, we kind of see this progression here. And so on the left, this is a acid with phenolphthalein. Phenolphthalein is an indicator used for titrations. And if we have a clear solution, this, if we see clear, clear means that it is still acidic. And that's why it is clear when we put it in an acid. If we see that bright pink, that means that we have something that is basic. And so we want neutralization. We don't want any extra acid or extra base. We want it to be neutral. And so that's why our goal is to just have seen that little bit of pink, but not go past that change point. And so a good pink indicates that neutralization has occurred. We would see a just barely pink, extremely pale rose color. And when you swirl the flask, which is kind of mixing it, it's going to stay that just barely pink. That pink won't go away. If the pink goes away, it means it's still an acid. So you would have to kind of add another drop. With titrations, though, they are going from that acid clear to that bright pink. Usually it only takes a drop or two. Once we get this really, really bright pink, that means we have a basic solution, and it indicates our reaction is not neutral. And so a dark, bright color, too much base was added. And again, if we swirl the flask and our pink turns clear, then that means that we didn't add enough of our base. It's still an acid, so we need to continue by adding a little bit more from our burette. So you are going to look at, through your lab this unit, you're going to look at this process, and so you'll get to actually see those changes happening. And so what does neutralization mean? It means we take an acid plus a base, we end up with only neutral products. And so that HOH, that means we're going to have water, and then we're going to have some salt, which is an ionic compound that is also neutral, because an acid, remember, has a hydrogen to donate. A base has an OH, or it accepts a hydrogen. And then if something's neutral, it has both an H and an OH, like H2O, or neither, like NaCl. And so again, our goal for our titration is for that acid and base to neutralize each other. So all of our H's go with an OH to form water. So we have no excess H's or OH's. And we only get neutral chemical products in our flask. And so in order for this to happen, the moles of acid chemical we use need to equal the moles of base with that. And so how can we use this information in a calculation? And so the titration calculation process is a couple of steps. In the standardizing HCl using titration pivot, you're going to follow this process and kind of do these one step at a time. And you can follow this process for every problem, or we do have a titration formula that kind of simplifies our calculations. And so you can use that if you're not necessarily going through the lab process. And so this process is that we calculate the volume of base solution used using our burette readings. So we did that in an example. Our volume of base used is our final reading minus our initial reading. And so we're doing these calculations after we've performed that titration process. So we have all of our data. Then we calculate the moles of base used because we know molarity is moles over liters. We know the concentration of our base solution in our burette. We know the volume used. We do need to get that into liters. And so moles are going to, we can find moles by doing the concentration of the base times the volume of the base in liters. After we know moles of base, well, we can figure out how many moles of acid we need. If it's neutralization, however many moles of base we have is how many moles of acid we have. So we're just taking this number, that's how much acid we have. And now we can use the moles of our acid and the volume of acid we measured in our initial lab setup. And we can calculate the concentration of the acid by doing moles of acid divided by the volume of acid that we started our titration with. And so these are all steps we know how to do, but there is a formula that kind of simplifies these calculations using that idea that our moles of acid equals our moles of base. And so we can kind of cancel this part out of both of these concentration equations. And so that titration formula comes from kind of what we talked about up above. And the titration formula is that the concentration of the acid times the volume of acid used is going to equal the concentration or the molarity of the base times the volume of base used. And so we've got two molarities, two volumes. And so we use A for acid and B for base to make sure that we are plugging those things in where we need. When using this formula, we don't actually need to get our volume in liters like we did up here because this molarity formula is based on liters. We can actually, as long as our volume measurements match, we can use either liters or milliliters. And for titrations, milliliters are usually what we measure volume in because we don't need a large volume in order to perform a titration. We can use a small volume like 10 milliliters of acid and get the same answers as if we had used more. And so with this formula, you will always know 3 of these 4 pieces. We can plug in what we know and then solve for that 4th variable, which is our unknown. So you're going to follow this process through the lab. If you want, you can go ahead and use this process on the examples we do. But in the rest of these notes, I'm going to just use our titration formula. So you neutralize, and anytime we see neutralize, that means that we can use that titration formula or titration equation. You neutralize 50 milliliters of an unknown concentration of hydrochloric acid with 60 milliliters of 1.0 molar sodium hydroxide base. What is the concentration of the acid? And so with this, looking at our formula, since this is neutralization, I'm going to use that MA times VA equals MB times VB. And so I like to organize my variables just to kind of pull out what I have from my problem once I recognize what formula I'm going to use, and kind of take this, write out my variables, acids and bases, and kind of pick what I know out of my problem and then figure out what my unknown is. So we've got 50 milliliters of an unknown concentration hydrochloric acid. So this is talking about our acid. So we've got 50 milliliters of our acid. We don't know the concentration of the acid. Concentration is molarity. And so that's going to be what I am looking for in this problem. It says it is neutralized with 60 milliliters of 1 molar sodium hydroxide base. And so then there's my base. And I've got 60 milliliters. The concentration is 1.0 molar. And so now I know I have 3 of these variables. I can find the 4th. we have our units of volume. Both of these are in milliliters, and we can actually leave those in milliliters because as long as they're the same, we're going to get that concentration out. I'm going to go ahead and plug in what I know and what I don't know. So I'm looking for molarity of A times 50 milliliters is going to equal 1.0 molar times 60 milliliters. As I look at this, I've got multiplication here. So how do I get that 50 away from the concentration of A or the molarity of A? Well, to undo multiplication, we are going to divide both sides by that 50 milliliters. 50 milliliters over 50 milliliters cancels. The concentration, the molarity of our acid then, we can get by doing 1 times 60 divided by 50. And I get a value of 1.2. Looking at my units, well, if we have milliliters here and milliliters here, those units cancel. And so that's why we can see that we are left with the unit of molarity, and that is the concentration, the molarity of our acid. All right, so I kind of have my setup on this next one. How much 1.2 molar hydrobromic acid do you need to neutralize? So we see neutralize, that means we are using that neutralization. We can use that neutralization titration formula to neutralize 75 milliliters of 1.5 molar barium hydroxide. And so as we're looking at this, we've got our 1.2, how much 1.2 molar hydrobromic acid. So here's acid. How much we are looking for volume. And we know the concentration is 1.2 molar. Do you need to neutralize 75 milliliters of 1.5 molar barium hydroxide? Well, those hydroxide is a base. And so those are going to be my molarity of the base, 1.5 molar and 75 milliliters. Since I can see I have milliliters for my volume unit, whatever I get out is going to also be measured in milliliters for my volume of my acid. And then I'm going to go ahead and plug in what I know. I know 1.2 molar. I'm looking for the volume of acid. I was given 1.5 molar for the concentration of my base and 75 milliliters. And then I'm going to solve to get the volume of acid by itself. And these are connected through multiplication. So we can undo that multiplication by dividing both sides by that 1.2 molar. Those cancel, giving me the volume of acid by itself. And we can go 1.5 molar times 75 milliliters divided by 1.2, noticing that our molarities cancel. And so when I go through and I do that math, I'm going to get 93.75. And then that unit, milliliters, is the volume of acid that I would need. And so this neutralization formula or equation kind of allows us to sort of find any part of that. We would, if we were doing this process up here, have to kind of switch around. Are we starting with an acid, a base? So there would be some reorganization of these steps. And so that's why if you have all that information, that titration formula is nice to work with. All right. If you feel confident, try this one on your own. This is the last one we're going to do together. You neutralize 10 milliliters of an unknown concentration of citric acid with 1.5 molar sodium hydroxide. So let's read the initial and final volumes from our burette. This is what we have that sodium hydroxide in. So our burette has the base in it. And so we're looking at trying to find the volume of our base. So initial and final volume, here's my initial. If I look at, again, that meniscus, I'm looking at the bottom. My volume initial, to me, it looks like that's right on the 10. And so I'm going to say 10 point, and because it's right at that 10 milliliters, I'm going to go 10.0 milliliters. So I'm estimating one digit further. I have markings to the nearest tenth, so that's why I said I know it's at 10.0 exactly. My volume final then, looking at the other burette, here's that. This one does look like, and you can see here, we let out some of that base to perform my titration. We got that perfect pink. And so now if I'm looking here, to me, this looks like we are a little past 21, but not quite at 21.1. So I'm going to say 21.05 milliliters. I'm not quite to 21.1, but I'm also not at 21.00 exactly. So now if we calculate the amount of base that was added through our titration, well, that's going to be our final volume minus our initial volume. So I've got 21.05 minus 10.00. And so it looks like 11.05 milliliters is how much was added. So now, what is the concentration of the citric acid? We know this is our formula, so let's kind of organize what we have. What is the concentration of citric acid? That's what it's looking for. The volume of acid, well, we are neutralizing 10 milliliters of that unknown concentration. So we have 10 milliliters as our volume of acid. Concentration, molarity of our base. This told us 1.5 molar sodium hydroxide. And then volume of our base, we just went through and found that from our burette readings. So this is my information. I have my milliliters matching, and so I don't need to worry about that. And I can go ahead and plug those in. MA times VA equals MB times VB. We're going to have MA times 10 milliliters equals 1.5 molar times 11.05 milliliters. As we then look at solving, kind of nice part about solving these is that because we are always undoing that multiplication, we just divide by whatever is with our unknown variable, or whatever's on the side with our unknown variable, we divide the other side by that value. So we're going to divide both of these by 10 milliliters in order to get the molarity of our acid. So as we look at that, I'm going to type in 1.5 times 11.05, and then I'm going to divide by 10, and we get 1.6575, and let's maybe round that to 2 digits after the decimal. So 1.66, and then that's a concentration. If you're not sure your units, just remember what you're trying to find, but milliliters here cancel, so we're left with that unit of molarity. That is the concentration of our acid. All right, go ahead and try example 4. I've got that one worked out here as well. I got an answer of 180 milliliters. This one, it was just asking you to find the volume of the base. Same setup. It's just that you would have just flipped what was in your burette, and you would be calculating volume of the base. For practice, there is a titration worksheet, there is a check-in, and then you will also practice this process in the standardizing hydrochloric acid via titration pivot. Reach out to your teacher with any questions.